So first of all, thank you very much for giving me the opportunity to talk through what we've been doing for quite a few years. And just because the material side probably is a bit sort of tedious, so I might sort of talking in a slightly higher level. So my talk probably will be sort of in three fairly short parts. I just convey some sort of key messages, which I believe is right, and secondly, I'm looking at sort of the concept and then give a couple examples if time allows. So first, I'll look at sort of heating and cooling decarbonization. What's the biggest challenges? I mean, so I'm going to start with sort of the diagram, which probably many of you have seen this diagram. So the key message of this is that globally, over 90% of energy budget centers around heat conversion, transmission, and storage, which means today thermal energy is at the heart, and fossil fuels does provide energy storage functions today, and actually the role of storage of energy is not very high today. So that's a message number one. Secondly, if you look at future 2050 to 2060 scenarios, I'm still using the same diagram, but I think that the fuels will become sort of a different combination of primary and secondary energy sources, including green, blue, or brown, hydrogen, for example, and renewable energy will be dominant. And I believe heat and cold will remain at the heart. And we know the renewable energy can't provide energy storage functions, and energy storage will have a greater role to play in the future. That's a set of the scene. So essentially, that's a sort of my thinking. Probably lots of other people are thinking as well. So the third message is if we look at from today to the future. So today we're using fossil fuels. Look at the afterwards is clean energy in the future. If you look at it from left to right of this diagram, then we have a few key messages here I want to convey. The first is, today and in the past, we have just a couple of energy conversion steps from energy source to our end users. And in the future, this will increase essentially in a fully sort of renewable energy world. So we will have probably up to 7 steps, conversion steps. We know every step has losses, and most of the losses into heat thermal energy. So which means we have to take efficiency as more important than ever in the past and today. So essentially, lots of people argue that renewable energy are free and we can use as much as we want. But the problem is efficiency. If efficiencies are low, then we will consume more resources. We take more lands and will increase infrastructure investment as well. So those are key messages. So another message I want to convey is global final energy consumption. If you look at the portion of heating and cooling is roughly 51%, and transport 32%, and power, which is electricity, 17%. Of course, we use power for heating and cooling, and we use power for transport, but our infrastructure does not take that. So essentially, the major challenge for energy transition to net zero 2050, 2060 is to meet the final energy consumption needs, which is predominantly thermal energy, which is over 50%. And I would say that probably will be more than 50%, as I will show shortly. So if you look at this, another scenario is that the economic growth versus the CO2 emission, then the bottom right is where we need to go to, but the developed countries like US, Singapore, Canada, they are on the upper right side, and need to bring that down to sort of a lower right side. So which would means that the challenge would be sort of how do we maintain our living standard without achieving while achieving net zero 2050, 2060. So that's a key challenge. So keeping our home warm, keep ourselves warm to resolve the energy poverty. That's just another challenge, and while achieving the net zero. So, so if I sort of going further, that's the UK example of heating using gas in winter. You can see there's a gas fluctuates a lot. If I summarize so in the table that from winter to summer, the electricity supply, there's a demand, there's a small change, from 600 to 1,000, and that's gigawatt hours per day. If you multiply by that, 360, you got roughly the year, which is about 330 to 40 so terawatt hours per year. But for heating, it's between 400 to 3,500, which is roughly 10 times. And transport it is still almost constant. So again, this illustrates the thermal energy is a main challenge for achieving the net zero 2050 to 2060. So and also heating is essential for cooking, for our heating, for washing. It's a basic aspects, but most important aspects of our living standard. So, and also last not least is the message is the cooling for the future. So if you look at this projection from around 2050 to 2060, the energy demand for cooling will be exceeding that for heating. And of course, partially due to the climate change. So essentially, if we don't take that into account, we will not be able to achieve the net zero 2050 to 2060, because we know the heating, accounts for about 50% of final energy consumption. If you add cooling, that clearly will increase that portion by maybe 60, maybe 70%. That depends on how you would calculate that. So we know cold chain is important, essential for food, for medicine, for quality of life, and hence again to maintain a standard of living. That's important. So that's the first part. Second, so I think the role, the leads for thermal energy storage, which is a lot of you already know that. I'll start from that as well. So this diagram, there is a technology for generation, for conversion, storage, and transmission distribution, and there's energy utilizing technologies. Actually, lots of those are sort of already there at a high TRL level, at a mature, although they're a lot less sort of economic sound, but lots of work, lots of R&D topics as well. So I think so basically, I want to illustrate from this is a few technologies which be used or emerging technologies which are regarded as sort of a magic bullet for the future. So I'm going to take sort of a couple examples. The first example is the electrification of transport, pure electric vehicles. Of course, those data probably is from a couple of years ago, maybe 3-4 years ago. There's some assumption for this. So if you look at this picture, what you can see is that the claimed mileage of electric vehicles is you can only achieve probably half on average, which means they are on very cold or very hot days, some 30 to 50% of battery power is for heating or cooling of vehicles. And we know onboard air conditioning units have a very low COP. 1.5, probably sometimes 1. And compared with stationary system of 4 to 6. So the question is, are battery powered heating and cooling solutions the best for EVs? I think the thermal storage can replace air conditioning on vehicles, and hence you can actually enhance the overall efficiency. And I think the weight for thermal store is probably similar to the air conditioning system. So that's a message I want to convey. So another thing is about hydrogen for renewable heating for domestic industry, which is electrification. This diagram is I produced recently, a couple of weeks ago. So if you look at a sort of 100 kilowatt hours of electricity produced for renewables, then you end up with a sort of for building application, if you use heat pumps, you probably can get over 200 kilowatt hours of heating. And of course, assume the COP of 2.5. Of course, in other applications, you could, for if you use electrical resistive heating, you probably get only 30 to 90%. Clearly, there's a work needs to be done. Of course, heat pumps are trendy technologies that have been still regarded as a magic bullet. But I think the key thing is they are not really for industrial heating. Industrial heating needs a high temperature, which the heat pumps cannot provide. So so essentially for building, that probably would work, but for industrial heating, you only have efficiency either 30% or if you use some other technologies, probably can be higher. So essentially, there are lots of work to be done. Of course, thermal storage has a great role to play here. So if I sort of turn back to the renewable energy for domestic heating using hydrogen again, so we from sources to consumption. If we use hydrogen economy again, if you assume 100 kilowatts hours of electricity from renewables, and you produce hydrogen. This is a sort of a 100 kilowatts hours electricity produced. You can produce about 55 to 71 kilowatts in terms of high heating value, and which means 100 kilowatts hours of electricity can produce 1.1 to 1.9 kilograms of hydrogen. And you have two options: either use a fuel cell and provide heat and power, or you also can combine that with heat pumps again. So the key message here really is efficiency is not very good, and for domestic heating using hydrogen. But hydrogen heating has value for industrial heating. So that's sort of message as well. So not everyone probably would agree, but I think the ballpark numbers are here, and happy to sort of debate on those. And another thing is, the thermal energy storage that has a function to play in the future is our sort of electronics, cooling, telecommunication, data centers, AI and autonomous vehicles. There's debate on Radio 4 this morning. I was listening. So, future vehicles, who is responsible if the vehicles drive over the red light? So is a supplier or the drivers? But interesting. But anyway, so it relates to it. So the key message here really is that ICT consumes about 10% of global electricity supply, and for data center cooling, the electrical supply will consume roughly 40% of for cooling, and most of those are waste heat. So again, the challenge here is how do we sort of increase the efficiency of data centers or telecommunication stations. And bear in mind, in 2030, we're going to, the ICT consumption of electricity will increase by about 100% to 20% of global electricity production. And this number will increase to 30% in 2040. This is not my prediction, but they're based upon a few credible sources, which is listed here. So many of you would know the storage technologies, and what I want to emphasize here really is the thermal energy storage has been de-emphasized, and we have not been doing a good job in advocating the actual fact, which is pumped hydro takes roughly 90%, which is no wonder about that. But non-pumped hydro storage roughly 10%, and batteries about 21%, thermal mechanical about nearly 80%. So those are the data, which is in summary, the thermal energy storage has a great role to play. So actually, those are reflected in the recent IRENA report, which is I led part of the technical part of the report, I'll just list that for power, for building, for district heating and cooling, for cold chain industry. So some sort of data shown here, I'll skip that, just which would mean that the significant growth in the future for heating and cooling using thermal energy storage technologies. So I'll leave some of those data here and just for you. So of course, if I summarize those data, and that's sort of a 2030 projection, which is will be a few times more than what we have today. So I'm going to get into the more sort of a technical side, which is about composite phase change materials. But so I'm going to sort of the physical basis of this, and then a very short overview of those. So first, what I want to say is that there's 4 fundamental phases and 8 phase change processes, and many of you would know that already. You have a guess solid liquid and the plasma. And if you look at this right-hand side diagram and pressure temperature diagram, so the phase changes, are illustrated by the red and the blue arrows, and of course there's some other phase change process within liquid, within solid as well. I'll show briefly. So essentially, changes in properties within a phase and a phase transition between phases require input or release of energy. That's the basis for this thermal energy storage, and so that's one piece of message. Secondly, is that the three major technologies, which is sensible heat storage and latent heat thermochemical, and some examples shown here in continental solar power, using molten salts, and we have a domestic heating from renewable energy using phase changing materials in large scale. And we have thermochemical storage for heating and cooling. So there's the right-hand side is a diagram roughly, illustrating what's today's state of ours. Sensible heat storage has been used for over 200 years, and from blast furnace, hot air stove, which has been used for many years. So the latent heat storage is said to be at TRA level 2 and 5. Actually, some of the PCM already had in large scale application. For example, the cold storage materials for cold chain transportation has been used for 30-40 years, and also in some demonstration as well. So, but overall, it's a medium TRL level. So, thermochemical, it's just at a fairly low TRL level. Of course, there's a couple of examples which is has a high TRL, and but overall, it's at a fairly low level. So I'm going to sort of mainly look at phase change materials. So if you look at sort of solid to liquid to gas phase, and those are processes illustrated already in the slides I put forward before. So, but if we look at sort of solid gas and liquid gas phase transition, they give a very large volume change, and hence are not suitable for thermal energy storage applications in most cases. Of course, the rankine cycle, steam generated, steam, the turbine power generation it's an application, but it's not for storing heat. So, but for the solids, liquid, solids and liquid phase changes, they are suitable. Of course, there's some differences. So if I sort of come back to this one, so essentially, if we look at a solids phase change, there are applications, potential applications, which is have very small volume change, but because small change and latent heat are not very high. In many cases, of course, in a couple of cases, you could also have high latent heat. And if you look at the liquid phase only, so liquid phase change, there are sort of a very small volume change and low latent heat as well. I mean, there's a sort of particularly in biological applications, the reconfiguration of polymer molecules, or the biomolecules. There's some sort of potential application in the future. So, and solid liquid phase change, volume change is fairly small, but not very small. Sometimes can be 30-40%, but the majority of the materials have a fairly small small volume change and large latent heat. So that's sort of so application of those, most of you already. So I've just shown that here. For there's lots of applications for both sort of a short-term and long-term storage. So I'll skip that. Just this for so we have phase changing materials. Why do we bother with the composite phase changing materials? I think those are the questions I'm going to list here. So first is this really for addressing major challenges in the use of PCM. And for example, the PCM for heat storage, solid state at room temperature, but fairly easy to store and transport. But if you look at the phase changing materials for cold storage, I mean, some in liquid state at room temperature, but some in gas state at room temperature. And so it can be challenging to store and transport, particularly so for the cryogenic temperature region. So there are challenges to address. And also some other technical challenges. There are shape stabilization, so both for heat and cold energy storage, because how do we maintain the shape stabilization? And thermal conductivity is the issue, and for some materials. And phase separation is a major issue for many cold energy storage materials we come across. Corrosion issues, both for heat and cold energy storage. Supercooling is a big issue for many cases, because, for example, our air conditioning system and the feed temperature probably about 7 to 11 degrees. Returning is about feeding is about 7, maybe returning is about 12, 11 degrees. So you have a very low temperature range for being integrated with the current air conditioning system. At data centers is the same issue. So cycling life is an issue, and particularly for organic materials and medium to high temperature heat storage materials as well. And we've seen lots of those issues after a couple thousand thermal cycles, and even for the salts for high temperature PCM, we see issues after about 3,000 cycles. So, and also for cold energy storage materials, there's microorganism issues, growth and moldy, and then so on and so forth. So those are sort of issues we have come across. That's just the reason why we needed it. So, I mean, clearly we define what's the composite phase change materials. I mean, you can see all sorts of definitions from the literature, and I'm not going to go through those in details. But fundamentally, the composite material is a material made from 2 or more components, and with very different chemical and physical properties, and the properties like unlike individual elements. Structurally, and the individual elements remain separate and distinct. Those are the composite materials definition. So for phase change materials, definitely is similar, but just need to have a function which is the phase change, and so that's a sort of but having said so, despite some similarities, composite phase change materials for heat storage are often formulated and manufactured in a different way from those for cold energy storage. And also composite phase change material products for cold energy storage have a very different microstructure and performance enhancement using different methods. So those are differences. I wouldn't have time for giving too much detail, but those finally, I think they are just let you know there's some challenges about scientific and technological challenges. The materials, component, and system integration still have lots of challenges. I will skip that. And scientific challenges is a massive sort of nanoscale problem, and tens of order of magnitude. So finally, I'm going to probably use 1 minute or probably for giving examples of CPCM applications. The first application is the for heat decarbonization, and we've been working on that for a very long time, and we have probably started this type of work many years ago. And so from material screening, you have to have different materials which are compatible physically and chemically, and good dispersibility when you mix them, and when you produce those, you have a good mechanical properties. Essentially, you have a skeletal material. You have a the heat transfer enhancement material dispersed in phase change material, and then form the microstructure and shape stabilized module. That's and of course those also causing manufacturing issues. And one of the methods we've been developing is have been used in conventional, the food production and minerals, and also the detergent and pharmaceutical, meaning mixing, shaping, drying, and sintering. So, and those are examples sort of from lab scale to pilot scale, and from semi-technical to production scale. So, just through sort of the last probably about 15 years development, so we have been managed to sort of make the materials at probably hundreds of tons scale per day capacity, and we have done quite a bit of demonstration, and sort of from very small scale, about 25 kilowatts, 100 kilowatt hours, to medium scale, which is 200 kilowatts, 200 megawatts hours, and to the first world first large-scale composite phase changing material application on the table near Kazakhstan and Xinjiang border, which is a 6 megawatts, 36 megawatt hours, which discards the wind power for space heating. So it's so today in short summary, high temperature composite phase changing material installations, there are more than 300 megawatts and over 1.5 gigawatts hours installation to last year. So so second application is the composite phase changing material for cold chain transportation applications. The idea really is to replace reef container like this shown here. If you look at open the back of this, you have this refrigeration system. You have a space inside for, and of course you have insulation materials. And of course the issues with this, you use diesel engine powered system and pollution issues, high operating cost because diesel is expensive and temperature fluctuation because of the nature of this refrigeration system and the control system. So, and the cold chain can be broken if refrigeration system fails. So the way we did it was, they just replace that with we use ordinary insulated container and we use phase changing material and we use a cold energy charge to charge those phase changing materials and use that for without diesel engine or refrigeration system. So we basically take a refrigeration system ground, or we ground refrigeration system. We charge the container, so the technology was supported by CRRC. We worked on it for about 5, 6, 7 years, and so the first generation was trialed in around 2018, and we had about 36,000 kilometers trial across different climate regimes, and in integrated rail and road transportation. Then 2019 we had a second generation, and now actually there are 62 vehicles functioning well across the region. So essentially one charge, probably you want to know, is that takes about 2 to 3 hours, but it can last for 7 days, and the operation costs was reduced by about 80% because electricity and off-peak hours are cheaper than the diesel, and also we have COP. System level COP is about 2.5 to 3 to 3.5. So that's sort of so here I'll stop here, and thank you very much for listening, and hopefully the time is sort of not too short. Thank you.